And our speaker today is Sean Taylor. Let me introduce you. Sean, big applause to Sean, please.
Thank you. Hey everybody, really happy to be here today. Excited to talk. Are we gonna get the... I made a slight change to the title of the talk, but nothing too dramatic. I'm working on a topic over the last few years called sequence analytics. It's a new domain that kind of inspired to work on through my history. A little life story for me. I did a PhD in information systems at NYU. I was trained as a social scientist, so I was really interested in studying human behavior, particularly how they use technological systems. And then after that, I went over to work at Facebook as a research scientist there, and then over to Lyft. Lyft is kind of like a competitor to Uber in the United States, for those who haven't been. And in those two jobs at Facebook and at Lyft, there's a type of data that I encountered really routinely in my job that I found very challenging to work with. And so that inspired me last year to start a company called Motif Analytics, where we're working on how to use this data more kind of fluently. And the type of data that I'm working with is called event sequence data, and it's kind of subtle because I think that this is a type of data that you're used to working with because it's the way that we create data in the first place. We log events that we create in the products and on the back end on the server side as users use products, and we create tables of lists of events that happen or transaction log, things like that. And typically we do some kind of aggregation before we analyze this data, and it kind of has a lossy transformation that makes it challenging for us to get all the insights that we can. And so what we're working on at Motif, and what I'm really interested in over the last year and a half and what I've been studying, is how we can unlock the value of this data. We're collecting so much data that we don't even get to look at, and the reason is that it's just too challenging to work with. And as we saw earlier in the first presentation, that when we know something about the type of data that we work with, for instance, that it's like from a network or a graph, there's lots of specific approaches that are unlocked by that. So for instance, for network and graph data, we do have a lot of different kinds of visualizations. We have ways of storing, querying, translating those data into insights, into pictures, into things that help us unlock the value of them. And we have this for a lot of other types of data. We have it for time series, we have it for spatial data, we have it for all these other kinds of data. But the most routine type of data that we collect, event sequence data, sort of has like been lost in the shuffle here. We aren't able to translate it directly into the insights that we would like. And I've been saying the word insight a few times. What does insight really mean? Well, to me, trained as a scientist, I think a lot about cause and effect relationships. And this is the companies that I work with in the technology business are often really interested in discovering cause-effect relationships between things that are happening within their businesses. And I came up with this taxonomy last year that I'm really quite happy with, which is like, these are a kind of space of scientific questions or analytics questions for within companies. And it boils down to basically where we live on this like cause-effect grid. So in some cases, we sort of have a known cause and known effect. This is like when you have a hypothesis that you go out and test. But a lot of people's business questions actually lie in the other quadrants where we have a little bit less machinery for analyzing them. So for instance, we might not know what the cause is, but we may have observed an effect. In cases where like, okay, like something happened, like we're having a bad quarter and we're not doing as well with our business. Why is that happening? What is the cause of the effect that I have observed? Or also maybe we've made a change and we'd like to know what the effects of it were. So we have unknown effects, even when we have a known cause. And then there's a kind of upper quadrant, which is like the realm of discovery. So like, I don't even have a hypothesis yet about a cause-effect relationship, but I would like to learn it from the data. I'd like to observe the world and understand something about it in order to derive like an interesting insight. So to think about how we might address these other quadrants of this spectrum, I think we need to go back to basic science and think about microscopes. Think about the tools that we use to take information that's generated by the universe and turn it into knowledge and information for ourselves. And typically it involves some kind of like focusing light on some specimen and reflecting it back into something that we can perceive. Something really subtle about this. And when we invent new microscopes or better kinds of microscopes, and I really like the Zeiss commercial that we watched before this because it's very much in line with this. When you have better optics, you see more things and you can observe more things and you can observe more cause-effect relationships. So we can think about a microscope as a kind of special case of a more general process where we have data, like for instance on a slide in a microscope, that we transform and then we convert convert it into something that we can visualize through different kinds of models and modeling techniques, and then we project it into two-dimensional space, or maybe three-dimensional space for video, and then we can kind of perceive what's happening, and it's an important piece of how we understand the world as humans and how we learn things. And it's very challenging to do with different kinds of data, and why we spend so much time thinking about how to process data and turn it into the things that we can then perceive. So this better perception problem is a really important piece of it. And think about this kind of like this joke from the internet. We have collected data at this very fine resolution. Event log data is extremely fine-grained, time-stamped up to the millisecond. And then we coarsen it and destroy a lot of information, and then look at it. And so the question is, like, where in that process of coarsening, of processing the data, are we potentially losing information? Are we losing insights, losing things that could allow us to learn the things that we want to know, that might be surprises, that might be generate a new hypothesis about what to do? So think of this as like, this is kind of a joke from an American show, but like in CSI, when they say enhance the picture, enhance the picture, enhance the picture, you want to go to a finer resolution, and to do that, we need to discard less information as we work with the data. So here's a picture of what kind of event sequence data actually looks like in a two-dimensional plane in its native form. So we take each event and we can project it into this two-dimensional space. So on the x-axis we have time, and it can be absolute time, like the time on a clock, or it could be relative time relative to some occurrence. And then on the y-axis here we have units of observation. Typically in product data, that's something like a user or a company, or something like something with a unique identifier. And we never really look at it this way. We typically look at it in a table where we have sort of like a column for a user ID and a column for a timestamp, and then a bunch of associated information. But we can project it into this plane and take a look at it. And in this particular kind of visualization, we don't get a lot of insights. But then what we do as data scientists and analysts and machine learning people is we turn it into, we do some dimensional modeling, so we do some aggregation. We just heard about that in the last talk, about how we might do a group by and then a sum, or a group by and then an aggregate. And that's exactly what most people do when they get data sets like this, is they take this, I'm not on the right side. They take this and we do like some kind of time aggregation. So very common analytics plots are where the x-axis is time and the y-axis is like a count of something or a rate. So that's this kind of like upper left quadrant. We do user level aggregations, and this is like featureization of a user's characteristic. So we kind of integrate now over rows of this data set and come up with like, this is the thing that we know about this user or about this particular user segment. And then we sometimes do both at the same time, and we create these decompositions of the data where we have like one time series per user or per user segment. And we use this to tell stories about what's happening in the data. And this is a very useful kind of modeling, and I'm not trying to tell you not to do it. It's what you can do in SQL very easily, and it's what most analysts spend their time doing. But what I want to make the argument for is that when you do this, you have already destroyed crucial information in the data set by removing the order of observations and the relative timing of the events. So to think about why that matters, we can go to a very simple kind of event sequence analytics problem, which is what people in finance and social scientists call an event study. Event study is, I think, the most primitive, simple form of analyzing event sequence data. And in an event study, what we do is we order the data and we take a sort of focal event, like an event that we think may have changed the time series in some way, changed the way that the process is unfolding. And it's very intuitive to think about. Like, events happen to us all the time, and they change our lives. They change the way we make decisions. We get new information. We get new choices, or we're affected in various ways. And it's a very common way to study things in the social scientists. So, for instance, when policies change, you could say, like, when alcohol laws change, what happens afterward? And that's a very common question to ask. Is what happens after this event? Typically, what would have happened if this event hadn't happened, and can we make a valid comparison between the two groups? And in product data, this happens all the time. So there's like, what happens after users enter new phases of using a product? Like, what happens after they sign up? Or what happens after they purchase something? Do they come back? What happens when someone experiences a bug or an error in our apps? Do we lose them as a customer forever? Or are they frustrated and stop using our product? What happens when people receive notifications and emails? These are all the kinds of product questions that people are really typically interested in. And they all basically boil down to some kind of event study. But what I want to argue is the event study is a really primitive and simple tool, and we can complexify it in a gradual way by thinking about users as existing in certain states. So let's think about a state machine or a state model. And the most simple kind of state model is a finite state model, where we have an innumerable set of states that users can be in. And then we have these kind of flows in between the states. So there are like events that trigger transitions in between the states. And those events are kind of like powering the ability of us to classify users as existing in certain states at certain times or not. And so in this example, we have a pre-event state, a post-event state that they transition to if event D is observed, and an outcome state which they transition to if event H is observed. And this is a generalization of that event study concept. So if we take the event study data, we could actually use this same methodology to study it. And what we're really interested now is the state transition into the outcome state. So like, does the state transition between pre-event and outcome happen faster or slower than in the post-event state? Another way to view a finite state model would be just to project it onto that same state space that I was talking about earlier, where we put time on the x-axis, we put states on the y-axis, and now users can kind of flow in and out of different states on the y-axis, depending on what state they are and what time. And in the original data set that we collect, what we can do is we can stream through that data set and event by event classify the user as being in a certain state. Why can't we do this with dimensional modeling? Why can't we do it by just taking user features and aggregating? It's because the finite state models are a recurrent, recursive, or iterative kind of computation that requires us to know the entire user history in order to place them in a state. So we have to know what state happened previously and what event happened and what state they're in previously in order to compute what state they're in now in the general case. So it can be a functional relationship, it can be a non-deterministic relationship if there are multiple state transitions. But in general, this cannot be done in typical SQL systems. So if you're working in a relational database, you need a recursive join in order to compute this, and it's actually very inconvenient and challenging to implement. This inherently iterative quality to classifying which state that a user is in has really prevented us from making progress on this problem for a long time. And people are gravitating toward using a Coarsen strategy in advance because the computation is simpler. But if you think about it this way, it's like we can do this step first, we can actually get the insights by doing this and then doing the aggregation. So go back to our event space diagram that I had listed at first. We have users in the event space. If we run this recursive algorithm on it, we can classify each user as not having events happen or not, but by existing in certain states or not. And then we can aggregate and visualize the data. And by doing this, we're able to unlock insights about what happens when users transition between certain states. So before I move on, I just want to show that like this, even though I showed a very simple state machine at the very beginning of this, that actually there are much more complex state spaces that are possible. So I used to work at Lyft, which is kind of like Uber, and we think about like a rideshare process, and like a user going through just the step from opening the app to getting dropped off. And a typical analyst at Lyft, we had something called the conversion rate of the ride request. So the user opened the app or had a session, and then they got dropped off. So we'd have denominator would be the count of the number of times the user opened the app. And the numerator would be the number of times that we had drop-offs, and we would compute that rate. It would be like 56% of these sessions converted into rides. But a very common question we would ask is why? Like, why is the rate higher or lower than it was yesterday? Why is the rate higher in this place and lower in this other place? Or why was it higher yesterday afternoon than it is today? And the answer is embedded in the flow between these states. So users can fail to convert, they can fail to kind of take a ride for all kinds of different reasons that you don't really know until you trace the path through the state space and try to understand at which phase were we actually failing to produce a ride. So there's a pricing phase where users can be given prices and they can decide not to take a ride because the price is too high. They can request rides, but then they can cancel the rides, or they can not receive a driver because the system's too busy. They can get drivers, but the drivers can cancel on them, and then the drivers can cancel multiple times, so they can exist in this state in a loop. And there's all kinds of things that can happen that are not even in this diagram. And so like by decomposing the data in this direction, rather than into a dimensional model, we actually can tell a much richer story of the things that are happening to users within our products. And so we have to take the data that we're doing and model it in this way in order to aggregate it. And if we model it this way first, we're able to kind of synthesize some more better insights about what's happening. I just want to make the point that I worked at Lyft, I also worked at Facebook, and I think that if you think about almost any company, the user journey that users go through, that they can be turned into these state spaces if we're willing to think about it and do a little introspection about what's happening within our product. So this is a blog post from the Duolingo's data science team. Does anybody here use Duolingo? I use it every day. I'm learning Chinese. They bug me like many times a day, and I exist in all these states where I'm like not quite ready to practice, and then they get me to practice. And they're very, very good at it. And the reason is that they've thought really carefully about all the states that users can be in their app. Like what kinds of users are there on our surface? It's not about what country they live in. It's not about what language they're studying. It's about what states they exist in. And the states are determined by their prior behavior in various ways. And so they have this whole user journey that they've mapped out. And for each one of these flows, there's an idea of like, okay, how do we encourage more of the good flows and fewer of the bad flows to happen? And so I think this is nice introspection. And when you go home and start using apps or products that you're thinking about, think about what state that the company thinks that you're in, because I think that will tell a rich story about like how they think about improving their products and detecting that they're maybe making regressions in their products. So let's talk about just how we analyze data from these kind of state models. Well, between any two states in a state model, there's a state transition intensity. And so you might think about, in the very simple case of a state model, it can be like a Markov assumption, and there's just a probability of flowing between different states. And we could think about, oh, what's the equilibrium distribution of this Markov chain? In event sequence data, the data have timestamps associated with them. So we need to enrich the Markov model to include the idea that like it's not just whether a user will transition between two states, it's how quickly that they will transition between two states. So if it's a good state transition, not only do we want it to happen more, we want it to happen more quickly. And so these typically look like these cumulative distribution curves where we have sort of like the user exists in state 1, and then they're going to get to state 2, possibly. They might not. They might stay in state 1 indefinitely. They might transition to a different state, state 3. But if they're going to go to state 2, we want to know the long-run probability of that, and we want to know how quickly it happens. And so these cumulative distribution plots are a good way to think about this. Is like it's an intensity of how quickly users transition between those states. So we can go back to that lift diagram for a second and think about, for each one of these arrows, there's a state transition intensity, and it changes over time, and it changes between users and between demographics, and we can overlay dimensional modeling on top of this, but that state transition intensity is the fundamental object of interest here. And I had this star down here to indicate that it's actually a little subtle what we mean by like whether a user will be in a certain state at a certain time, because it could mean that they end in a state. There can be like one-way state transition flows where users kind of end in a certain state and need to be there indefinitely at the end, like for instance, like a purchasing funnel where a user makes it to the end or they don't. But there's also kind of users existing in a state for longer periods of time. So if you have good states and bad states in your app, and you have an app where like engagement or user satisfaction is most important, it's not about whether they get to an end state or not, it's about whether they exist in the good state for a longer period of time, much like the Duolingo diagram, where they sort of like want users to be happy enough to be using the app on a regular basis. So to think about that kind of like existing in a good state or a bad state, we get into the realm of loops within the state machine. So if they're just directed graphs without loops and they're acyclic, it's a little simpler to think about because it's all about just paths. But when we have loops, then users can kind of transition back into certain states. So now it's not less about the intensity of whether they get to the state or not, but it's about existing in certain states for as long as possible that are good, and not existing in bad states like a customer who's dissatisfied with your product for as short as possible. So we can kind of like take this diagram and unroll it and figure out how to count up all the possibilities of a user existing in certain states at certain times, and we want them to stay in the good states for as long as possible. We can, and the diagrams now can have like they can go back down. So it's kind of like an excitation process where they can kind of like become more excited and then less excited over time, and it can kind of like loop around. One of the most powerful things that you can do with a state model is to apply your domain expertise to take the states and map them into scalar values. If you apply value modeling to the state machine, that you can now compute things on a y-axis that makes sense and can make business value sense. So that if we say like, hey, getting to this state is worth $10 and going to this other state is worth negative $5, then if I'm in the first state, I can actually compute the probability or the expected value of being in these future states and then multiply that probability by the value and get the expected value of that state, which is a very powerful thing to be able to do. It's like, what's the value of a user in this particular state? And even more powerful than this is the value of the transition between two states. So how much should I really care about users transitioning between states 1 and 2? Well, if the expected value of the difference between those two states is very high, then I would say, hey, this is the kind of state transition that I would like to really encourage or discourage if it's a negative value. And so by assigning values to the states, we're actually able to turn these probabilities and these state transition intensities into something more business interpretable that can be used to understand and gather better insights. So one of my favorite examples of this methodology applied is in sports, and this is for American football, which is my favorite sport. There is a state to every game that you can think of. In any game or any sport, there's a state space, and users exist in it. The game exists in a certain state. And each of the teams that are playing in the game would like the game to end in the state where they have won the game. And we can assign that thing, the winning the game, to value 1, and then we can go and compute the expected value of being in every state at every point in the game. So this is my favorite team, the Philadelphia Eagles, playing in the Super Bowl a few years ago against a different team. This is the probability of them winning the game based on what we know about the state space at the time of the game. And so they take historical data from football games and say, like, when teams tended to be in the state, what was the probability that they went on to win the game? So this is a fun graphic to look at, and you can kind of see how interesting this game was, and you can get insights about like who was winning at various times, even though the game hasn't really finished yet. But I think most powerfully is that you can take any individual event from the game and quantify its value to the team. And so here, this is the most pivotal play in the whole game where 20% win probability was added through this event happening. So we know the state was the score, what position they were on the field, how much time was left in the game. And then this event happened, and then they're in a new state. And at the end of that new state, the probability of winning the game went up to 96%. And this is like a really powerful attribution technique. It's like for any event that occurs, we can give it a number and say, this is how important this event was in determining some business outcome for something that you're particularly interested in. It also allows you to filter out data that's uninteresting. So if events occur that don't transition between states, or they transition users between states where the value does not change very much, then you can kind of ignore them. They're safe to ignore. So it's a way to kind of shorten event sequences to only the ones that are most meaningful. So the finite state modeling technique that I described to you is a special case of a continuum of state models that we might employ as data scientists and machine learning people. So on the very right-hand side, I would say call these like lower dimensional representations of data where we compress it into very, very small numbers. So for instance, just like a count divided by another count. So we compress it into two numbers and we divide them. It's a very high bias, but a very low variance representation of the data. And this is what we gravitate toward in the analytics world, is a simplification of the data, so much so that we can compress it into just a small number of numbers to say like how well this process is working. On the very high dimensional side, we could actually just look at the raw data itself, but there's too much data. It's like, we can't compress that into an image or even make any sense of it. And what we're trying to do is trying to strike a balance between these two things, where we apply a model to the data that doesn't destroy too much information and retains the things that are most interesting, but also synthesizes the insights that we want. And so the finite state model that I described is just like one point on this continuum. And the states are interpretable and editable, and so this is a really nice human-in-the-loop process. And the only problem with it is that we don't know if this doesn't work very well for like unknown unknowns, like things that could be happening in the data that we don't know about yet, that we haven't been able to kind of like create the right states or the right state model for. And so what we've been working on at Motif is using a deep learning model as this intermediate step. So we can compress the raw event data a little bit, but not a lot, by fitting a sequence model to the original data. So I'm going to talk a little bit about how we do that. Okay, so on the left-hand side, everyone's familiar with LLMs, and I'm sure you've all used ChatGPT, and it's very exciting technology. And what's really cool about it, to me, is how simple it is, actually. It's just like we're just taking sequences of tokens and trying to predict the next token, and we just do that over and over again, and we do it at such large scale that we're able to create these summaries of the data that are very, very powerful. And so what we do is we train a language model, and then there's a fine-tuning step where we try to make that language model do the kinds of things that are more interesting for the tasks that we have in general. So we put in a prompt, the model spits out something that we're interested in, usually generated text. Sequence data from event sequences has a very similar structure to text data. It's just that it has additional information. So instead of a word, we have an event, and the event has a timestamp. The event has additional metadata associated with it. But it's still applicable to the same technology. But we have to think about it a little bit differently, because in text models, it's useful to summarize the model by having the model generate an example for you. So when you type something into ChatGPT, and it sends back a response, that's the model's output. It's like an example from the probability distribution that it has modeled. If I were to train a model on event sequence data and have it generate a new event sequence for me, it wouldn't be very interesting. I can't like look at log data and get any insight out of it. What I needed to do is actually predict an aggregate instead of predicting an example. And so this is like a subtle difference between the two. The second difference is that I need to tune the model not on making some kind of specific kind of output, but on knowing what is interesting for me about the data set, and I call this value tuning, or trying to figure out what is up and what is down in this world, and how do I figure out how to tell you the things that are more interesting. So another way to look at what's happening when you're training a large language model or a sequence model on event data is we're trying to come up with an embedding space for the event sequences, for the entire user's path through the product or through the experience that they're operating in. So we can think of this embedding space as like this kind of like latent space that we don't observe. And every user at the very start of their sequence starts at some point in that space. And after each event, they move within that space to a new position, to a new position, to a new position. And they sort of traces out a path throughout the space. So after every sequence of events, at any point in that sequence, the user exists at some point in this embedded space, and that this embedded space is a rich representation of the entire user's history. So it's kind of trying to compress everything that's happened to a user into a single multidimensional vector of fixed length that we can then work with within a machine learning algorithm in a more fluent way. So just to kind of make this concrete, how this works is if we have a transformer architecture, this is like what everyone would think of when they're thinking about training large language models is a transformer with an attention mechanism, causal self-attention. We're taking a set of events, and each of those events needs to be encoded into some event space. And then we're going to use an attention mechanism to compress that into a position vector, which is the sequence embedding of the entire user's history. We can use that to predict the next event probability and then compute a generative loss on top of that for the next event probability. But what does fine-tuning on values really look like? Is we take that same model, but instead of taking that event sequence embedding that we use to predict the next event, we use it to predict what happens in the future for that user, over the full course of history for them. Like, will they be a customer 3 months from now? How much revenue will we make from them? How many times will they use the product? We can use all these things as labels in a user-specified value function and use that latent space and project it onto the space of things that we care about in terms of business outcomes. And the only real trick that you need in order to use this technique is to think about text needs to be embedded into embedding space or encoded into an embedding space first before it can be applied to large language models. The same thing has to happen for events. We have to take events and encode them, and we can use it through either concatenating individual fields of the events, or we can actually use the same embedding space for all the event fields and think about each thing that we know about the event updates the user in the position at some point. So we can take this sequence modeling task and think about it as, like, we have this observed event sequence. We can think about a counterfactual event sequence. So, like, what if this event didn't happen? Or what if a different event happened next? And you can start to answer questions like this with a model like this. It's like, what would happen if a different event happened to this user? Or if like, you can think about all kinds of counterfactual situations. And this model can answer those questions once it's trained. And you can use this model to gather insights. So I'm running a little short on time, so I just want to quickly mention. Now, like, within this methodology, what is interesting? How do I surface something interesting for the user? The key is that you have to define what is an interesting event? What does an interesting event mean? And I think that one definition that I think is quite compelling is to think about an interesting event is one where after we observe it, the long-term probability of something for the user has changed fundamentally, just like in the football game that we talked about. It's just that in the football game, we sort of knew the state space in advance. And in this world, with the machine learning model, with the deep learning model, with analytical AI, we've taken all the historical data and embedded it into a latent space that we don't observe, and then gone to answer this question of when has the probability of some long-term outcome meaningfully changed for users? What events have caused that to happen, and when can we go and look at it? And these are the things that we want to look at as data scientists. So I just want to show you what this looks like in practice, so it's not all like theoretical, and we're still very early in building stuff like this, but I think it's quite compelling to think about some example use cases and when it might actually come in handy. This is an example of actual data from one of our customers, and so these are events that are kind of laid out in this particular coordinate system that I described at the very beginning, and it's a very low bias, high variance visualization without a lot of structure. And if we cluster the sequences in the correct way, a lot of structure pops out of this sequence. There's a lot of users that have very similar user journeys to one another. And so we can kind of look at this diagram as telling us like what happens most commonly to people in this certain situation. And vertical space on this diagram is proportional to the commonness of the situation for the user. Then we can overlay this diagram with events of interest, so events that generate value. So for instance, we assigned value to certain states earlier. Well, what if the value were labeled in this diagram? This is what it would look like. And you can see this is why we have a big challenge with dimensional modeling, is that the outcomes of interest typically are quite sparse. And what we really want to do is use the machine learning model to fill in the blanks here. Like all this white space here is telling us like nothing interesting happened until this thing happened. We actually know a lot about what happens beforehand by applying the model. So now when we label it with the expected value of the outcome instead of with just the outcome itself, we get like early warning signs of users where the value is about to tick up or tick down. And so it gives us kind of like which events actually mattered before the thing that happened was observed, which is a valuable thing on its own. But many of the sequences are uninteresting. So one of the things that we can do very quickly is to filter to only ones where these are event expected value distributions that are flowing over time are the ones that varied in a meaningful way. So we can focus on users where the user journey was interesting, where it did vary in some way. So we kind of like, you can think of this as a zooming operation where we zoom in on the sequences that are most interesting within our data set. And now we get like a really nice picture of all the interesting things that happened to our users, or the users who had interesting journeys where the value did fluctuate for them throughout the sequence that we observed. And then we can take the first differences of that visualization that I just showed you and look at where is there high contrast regions? Where did that probability increase or decrease? And in an exploratory visualization like this, which is built into our app, you can actually zoom around and find the most meaningful events, like where did the probability or the expected value of this long-term outcome meaningfully change for the user, and go and look at the specific sequence of interest and see maybe why, which is a really nice and powerful technique. And I think this pairs really well with domain expertise. So this is a very raw look at the data. It's exploratory. It's meant to generate hypotheses. And people who are domain experts in processes who actually have created the logging data, created the infrastructure, are able to kind of look at this and glean insights about where there are pivotal moments and interesting patterns in their data. So just to wrap up, I think this is a really powerful way to think about data. I worked with event sequence data for a long time, and only after spending the last year thinking about it in a deeper way have I really been able to figure out that the big problem that we've had the whole time is a representation problem. How do we represent sequences as something that isn't too hard to work with, isn't just some long list of numbers, but actually kind of is encapsulating the insights from the data? So in order to do that, we need a kind of idea of like, what state does a user exist in at every time, and what is the state space? Is the state space a finite set of states that we articulate from domain knowledge? Is it a continuous latent space where we can kind of embed even more information in the data? So we can use either one of these two techniques, and they both have their strengths and weaknesses, but we need some kind of representation of state space in order to make sense of sequence data, because the raw data themselves are just too high variance for us to look at. So these state models are very, very good models for sequences. The hard part is evaluating fit, trying to understand if they fit the data well and are functioning well. And the other hard part is assigning values. So you really need to have some domain knowledge in order to do that and project it into a coordinate system that you can actually visualize in an easier way. So with that, I'm going to wrap up, and I'll take any questions that you have. Thank you.
Thank you very much. Thank you for this really great presentation, very inspiring. We already have 2 questions. Don't forget to vote in Slido, and don't forget to put your questions into Slido. And first question, what type of database supports this type of even state analysis?
Good question. One of the interesting things about event sequences is that they're very easy to store using relational databases. So any SQL database is very good at storing event sequences. But querying event sequences the way that we described has been a big challenge for us, and the SQL databases are not very good at that. So actually at Motif, we've been building our own query engine and query language for querying sequences. as a way to remedy that. But I think in general, it's sort of like that you need to write code to serially process the sequences, and most databases aren't very good at that. So the difference between storage and querying is very important here. And the querying thing, I think, is a part where we just don't have great tools right now for doing that, and that's something that we continue to work on.
Sounds like there is room for research.
Yes.
Could you elaborate more on the exact target prediction and loss functions you are predicting in a deep event model? This distinction between the language model,
Right. Yeah, I think that the relationship between large language models and what we're doing is quite close in that, like, in general, the reason why those models are so successful is that self-supervision is a really nice technique, because you always have a next event or a next text token to predict. So you have a really rich data set, and so predicting the next event is usually what those models target, and they're able to organize the data by always trying to predict the next event. The problem with that is that it's not a long-term perspective about what happens at the end of the sequence. It's very myopic. It's like thinking, oh, I need to know just what happens in the next event. And the next event might not be very meaningful. What I really want to know is what happens to the user in the long run over some longer time scale. So what we do in our training is try to pair those two ideas together. So try to pre-train the model using the self-supervised objective, for which we have a really rich data set. The longer term examples tend to be sparser, harder to come by, so we use a second fine-tuning step to train on those long-term outcomes, where we try to take the same model that's already been pre-trained and then train it on the longer term outcomes. So usually the user provides like a variety of different outcomes over some window over the next thing, and then we can use a typical kind of like mean squared error loss function for that training step.
Thank you. Next one, could this be used in predicting usage of large real-time systems?
It's a good question. I think the real-time part, the only real challenge is that there's a lot of latency for the deep learning models. So like the inference step where we're performing inference is still on the slow side. So I think for real-time systems, it might not quite be appropriate yet. The same reason why when you type into ChatGPT and you wait for it to generate tokens and it takes a little while, we have a similar problem. In particular, the attention mechanism is the hard part. So we have to look over a whole context window and compute the weights, and that part takes a while. Once you have an event embedding the state space that you're in, projecting that into the value function is actually quite fast. But the part where you say, hey, this whole window of events all contributes toward what state that the user's in at this moment, it takes a lot of computational power to do that. So I don't think we're ready for real-time applications just yet.
Maybe I can add on a little bit on that, because I think this is also depending on how large the data set is.
Yes.
So in smaller data sets, actually, we have applied it in computer technology to do this.
It's great to hear.
Next one, how to extract the state machine from the data?
Right. Yeah, I think that we're thinking a lot about how to make these techniques more accessible to users. And really, fundamentally, like the states that the user are in is a coarser, smaller data set than the events that happen to the user. So I showed some examples of what the tables look like. But really, if you think about it, you're streaming through an event table and labeling state transition moments. But many of the events, the user just stays in the same state. So the way to make it accessible to users is to just take that event table and turn it into a state transition table and provide that to the users downstream. So it's actually quite straightforward to just like filter the table to only times when the state's changed and provide that. And that's a coarsened version of the data that then you can visualize and model in other ways.
Mm-hmm. Thank you. Next one. There are many questions, so I try to be quick in that. Could by any chance blockchain improve the storage of the sequences?
Could the blockchain? Oh, wow. I hadn't really thought about using a blockchain for this.
Surely it would introduce some more computation, I guess.
Yeah, I mean, I guess I'd have to think about why instead of a database, and I can't think of any compelling reason, but it's an interesting thought for sure.
Thank you. Next one. Sounds like building such model is highly dependent on the background knowledge. Are there best practices to filter correlation from causality? Yeah,
I mean, I think of those as really two separate questions. Like, yes, domain knowledge matters a lot here, and I think like anytime you're working in analytics, it's very. I think it would be almost impossible to say a person who has no domain expertise could use this tool and get some insights. I think domain expertise is a prerequisite for learning from data in general. So I think that it's really important. And when you think about the causality aspect of it, none of the data that I'm showing you or working with at this point is like has an experimentation built into it. I think like making causal claims from data sets like these tends to be pretty challenging. But if you weaken the argument a little bit and say, like, I don't need to have a true causal effect, I just need to generate a hypothesis about a potential causal effect, I think that we can do that. And then you can go and take that hypothesis and go test it in a more rigorous way. So when I think about causality here, is really a step before you run an experiment or a step before you do a rigorous causal analysis. Is just having the idea about what causal analysis to do in the first place. And we're really trying to work on that problem.
Mm-hmm. Next one, do you see only, do you use only historical data for the projection or future expectations as well?
Only historical data. Yeah, I think that one of the nice properties of this whole process is that if you have a position embedding in a sequence, it compresses all the information that we know from the past. So there's no sense in which another model or any other information is necessary for predicting what happens next. It sort of has already synthesized as much as it possibly can from all the historical events. So like, it's a big advantage over systems like this from like traditional modeling techniques. Like what we heard about in the last talk, which is great, is that like you build all these features and you use them to train a lot of different kinds of models that are special purpose. In this setup, you're creating one vector that represents an entire user's history, and you don't need to do any feature engineering, and you don't really need to do any modeling. The modeling step is quite trivial, but you're spending all your upfront effort trying to organize information about where does the user exist in the state space at this particular time, and then the modeling becomes quite simple after that. So we don't need to think about like incorporating other information from other models.
Mm-hmm. Thanks. And two last questions. In the real world, the available states come and go. How would you account for that?
Yeah, that's a good question. And I think that in a lot of ways, we view this as an ongoing modeling exercise. There's no one model for your data in a sequence modeling context. I think the model evolves over time. So at Lyft, when I was at Lyft, we added new ride types. We added new steps in the process. So the model is going to be an evolution. And in our product in particular, we have a very opinionated view that model checking and validating the model is actually one of the most important steps in the process. So it's not just writing down a model, but it's seeing that it fits the data well. Like if you have states that users never enter, then the state doesn't matter. And if you have states that users are always in, then that state's not very useful either. So you need to kind of iterate on the model over time and change it when the business conditions change or when your business changes in various ways. And I actually think a lot of small models that apply to very specific situations for users is probably a stronger technique than like one big model of the entire business process. So we very much think of it as kind of like a human-in-the-loop iterative modeling process with a lot of feedback about model fit and model evaluation as being a really important part of the process.
Mm-hmm. Thank you. And the last question, but not least, how much transformers are better than simple aggregate features?
This is a fantastic question, because the question is like, why do we go to all this effort to train transformers and do like a really do this kind of crazy modeling? Part of it is that it allows us to circumvent a lot of steps that would normally need to be taken. So even if the performance were about the same, it's convenient to not have to think about building any features because we get to skip that step and just consume the raw event data. And so we don't need a feature store and we don't need a lot of things. And so it does simplify things. But in general, the performance has been very similar. And part of the reason we suspect is that many of our clients are working with relatively short sequences, and that a technique like this tends to work well with longer sequences where you observe a user for a longer period of time. And so we're hopeful that with longer sequences that we'll start to demonstrate some performance benefits. But for now, just the simplification alone, I think has been a big benefit to us to be able to like just one model that organizes your data and then a lot of really small models that project it into value space, which are very simple to build.
Thank you very much. So this was Sean Taylor. And thank you very much for your presentation. It was really great.